Let's get started. I wish you a happy new year and hope this year will bring you happiness and success, not just in academic work but in other areas as well. Right, so before we get started, a few things. I have circulated the attendance sheet. Please write your first name in the first column. There's a space. Write your first name in that column. That's not the signature. The name you want me to call you. Write the first name. And also, if we have, if you guys have Monday 10 to 11 lecture free, then we can advance this lecture to 10 a.m. I will talk with Professor Godliadda and see if he is taking any discussion classes. If not, we can advance the class to 10. I will let you know and I will keep you informed through the WhatsApp group. Especially on the 12th, I would like to start the lecture at 10 because I have to leave early to go to Colombo. So that's that. And a small correction from the previous lecture. I think a couple of students mentioned this. When I gave the BJT active linear mode model, I have indicated that slightly, not slightly, it's wrong. Right, if you go to the external energy model with active linear model, I have given the BC transistor, BC diode as short circuited and with the forward drop 0.5 volts like this. So what I have given in the lecture note is something like this is what I have given you, right? But obviously base collector is reverse biased, right? So this should be open circuit, and besides, if you have this is 0.7 and this is 0.5, irrespective of what is there, the voltage here will be 0.2, right? That is wrong, right? In active linear region, what you should have is whatever the voltage that is determined by the other circuit. So therefore, the current is what is being controlled here, right? Beta times IB. So therefore, kindly make sure that this should be corrected as open circuit, right? So this should be, the correct one should be something like this. Okay, so make that correction. That is wrong in the handwritten lecture note as well. Please make that correction. Right, thanks. What's your name, please? Pahasarani. Right, so kindly give your E number at the end so that I can give you due credit, right? Okay. Okay, so let's move on. Okay, so we have been discussing about different models of MOSFETs. Basically, we started to look at the 3-terminal switch mode, right, this model of the MOSFET. And before that, we talked about various models of the BJT, starting from very simple back-to-back diode model and how to replace this to make it more accurate when it operates in the active linear mode, right? So we looked at them and then we started to look at the ideal switch mode for the MOSFET. Any questions so far before we move on to other more detailed and more advanced models of the MOSFET? Also, I have now made the lectures available through YouTube because the lecture video files were huge, like 3 GB and 6 GB. So I thought it makes it difficult for you guys to watch it online using that. But now I think a lot of you have the packages for YouTube, so YouTube video is now available. Besides, if you want, you can watch it at lower resolution, right? So all the lecture notes will be made available through the YouTube channel. Kindly, there's a video list, so go through that. Okay, right. Let's then move on to the next model, which we call now. Earlier we had on and off. During off, no currents flow. During on, there's a current through source, drain to source, and we assumed it's an ideal short circuit, which means there is no voltage drop across source to drain. But in reality, that is not the case. There is a voltage drop. It's not a short circuit. So this is to better capture this. We in the next model we are going to put a resistance, a constant resistance to model that voltage drop. So therefore, the next model we call switch resistor model, OSR model. So we have during the off state, nothing is changing. So you will have something like 3-terminal device, drain, source, and the gate. And the voltage applied here is low. In other words, V gate to source is less than a particular threshold voltage Vt, right. So under this off state, so this is the off state, it was the same thing as the previous model, nothing changed. But in the on state, we are going to modify this. Instead of earlier having just a short circuit here, now we are going to have a resistor R. We call this R on, drain, source, gate, and here IG is 0, ID is also 0. Here VGS is greater than V threshold, this is not V threshold, so therefore this is high, and this current is IDS. Now it's not 0, that's the current, and the voltage here is VDS, and that value is not 0 any longer. Earlier in the previous model that was 0. Now here that value is equal to IDS times R1. Okay. So this is the new model that we have. So to represent this, we can have the VI characteristics. This is the VI characteristics. This is VDS, this is ID. During the cutoff region, there is no change, right? Cutoff, no matter what voltage is applied, as long as VGS is less than the threshold voltage, this current will be 0, right? So this is cutoff region. Where VGS is less than V threshold. Right, so that is cutoff region. Now initially for the switch mode, we had during the on state, we have no matter what is the voltage, as long as VGS is greater than or equal to VT, current can vary without a voltage drop. Now in this case, as the voltage drop is ID times R on, what we have is kind of like a resistor model. So it looks like this, as constant slope. So let's make it like this. That is the for VGS greater than or equal to VT. This is the model that we are going to use. We call this the triode mode. Triode mode. This is the triode mode or triode region, and the slope of this one over R on. And we can write the equations of ID or IDS, drain to source voltage, drain to source current, 0 when VGS is less than VT as a cutoff. But when it is greater than, then this is basically VDS divided by R on. Okay. For VGS greater than or equal to VT. That's the SR model. And similarly, we can get this is the VI characteristics. The other characteristic that we are looking at is the transfer characteristic, the input output characteristics, right. So, transfer characteristic. That is V out, V in. So, what is V in? For this transistor, what we have is something like this. VGS IDS VDD over here. So, what is the input and output? We take the input from here. So, this is my input and this is my output. So, V in is actually VGS, V out is VDS. Okay, so that is the characteristics, and we know if the voltage is less than VT, VGS is less than VT, that is this condition, ID is 0, does not matter, but because ID is 0, there is no voltage drop across this. So, the voltage here will be the same as VD. So, VDS is equal to VDD minus ID times RD, right. So, that is the equation from Kirchhoff's voltage law. So, therefore, when ID is 0, VDS is equal to VDD. So, this is VDD up to this level, that is off, this is the off state, right. Right, when it is on, ID we do not know, but we know that VDS, what you have is then instead of this you have a resistor here, R on. So, therefore, what you have here is simply a voltage divider, correct. Instead of this transistor, what we replace it with is this model, So you have a resistor there. So you have two resistors. Vd is connected to that. So therefore Vds is equal to Vdd times R on divided by R on plus Rd. Right. So that's a constant. Vd is a constant. So Vdd is a constant. R on is a constant. R on and Rd is also a constant. So this is a constant. So therefore this value should be a voltage around here. That will be Vdd. Sorry, Vdd times. Sorry, this is Vdd times. Vdd times R on plus Rd. That value. So that will be the same value throughout. So this is my transfer characteristic for that. The difference is earlier this was on here, right? There was no voltage drop, it was at 0. Now there is a constant voltage drop. This is the difference between the previous model and this model. Any questions? It's simple enough. Move on. So in reality, even this model, for certain cases this is good enough, so we use it sometimes, but that does not capture some of the important features that we really use the MOSFET, especially when we use the MOSFET as an amplifier. We can design amplifiers using MOSFETs, but according to this model we can't properly do that. So to do that, we actually use what is called the switch current source. Instead of a resistor, we are going to use it as a current source. Why? Because there is a relationship between VGS and IDS. It will, if you can remember, we will put it down. Switch current source. Switch current source model. Because the MOSFET behaves like a voltage controlled current source. What is the controlling signal? VGS. Depending on VGS, output current varies, IDS. So MOSFET behaves like a voltage controlled current source. When this is not always, just because VGS is greater than threshold voltage will not behave like a current source. This is also when, yes, VGS has to be greater than or equal to VT, so that it is in on state, but in addition we also need VDS, the output, to be greater than or equal to VGS minus this threshold voltage, which we call this V overdrive. We call this overdrive voltage, right? If VDS is greater than this, right, then we have, when this overdrive voltage is positive, we have this like that. Then there is a relationship between IDS and VGS, is K divided by 2 VGS minus VT, the whole thing squared. Now you realize that this term is nothing but this, right? So this is basically K divided by 2 V overdrive squared. It's a square relationship. You will see that this is related to the input voltage Vg. Okay, but there is a offset. It's not VGS from 0. VGS starts from Vt. Anything below that anyways this is off, right. When Vgs is equal to Vt, that is overdrive voltage is equal to 0, the current is anyways 0. So, at that point and below that region the transistor is off. So, that up to that point it is not behaving like this, it is a switched off switch, right. So, when this happens, this is what happens. So, therefore, we represent this, initially we represent the off state similar to what we already have. Right. So, this is off state. Vgs less than Vt, right. On state, now we have a current source. And this voltage is Vgs, and that is greater than or equal to Vt as the input voltage. The output voltage Vds and this current I ds is equal to this equation, k divided by 2 Vgs minus Vt squared. So, that is the relationship. So, it is a function of, so Id is a function of Vgs, the others are constants, correct. That is what we have there. And this k is something depends on the construction of the MOSFET. K depends on the construction of the MOSFET, like the width of the gate, length of the gate, and the gate oxide thickness, that kind of things, right. So, in the this K is equal to K in W over L, where W width of gate, length of gate, and Kn depends on gate properties. Such as gate oxide thickness. Okay, so, those are all, once you manufacture the MOSFET, they are not going to change, right. So, that value is a constant. So, that is basically this K. And now, if you draw the Vi characteristics, for this particular model, so you have IDS and VDS. Obviously, the cutoff is the same, does not change that. Cutoff is the same. Earlier we had, in the switch mode, we had something like this, right, on off mode, and for the switch resistor mode you had something like this, but for this one it's slightly different. Now, if you look at this particular equation, ID versus VGS, right. So, if I now, in order for this to actually operate, this condition has to So VDS has to be greater than this. So what is VDS? That's the VDS axis is this. What is this? VGS minus VT. So if we have a VGS value here, VGS minus VT is just this part, right? So if I draw a curve and the current, so if this is my overdrive voltage, if VGS is here, VGS minus VT is that part here, ID should be proportional to square of this. So from at this value is 0, VGS is equal to this value, that value will be somewhere here. As you increase it, you will have a exponential, quadratic relationship like that. This is a quadratic relationship. This is basically ID equals, IDS is equal to VGS minus VT squared. On this curve, on this particular curve, right? That curve represents this equation, right? This curve basically represents this curve, assuming in this side we have VGS, right? But what we have here is not VGS, VDS, right? So what is VDS on this curve? This curve, VDS is equal to VGS minus VT. Okay, on that's the curve. That curve represents VGS minus VT. Okay, so according to this statement, this relationship, whatever that you have, this behavior, current source behavior, only applies if this is greater than VDS. That is, VDS values should be bigger than this. That's anywhere here. Anywhere here it's okay. If it is this side, VDS is less than that value. So it won't work during that time. For this side it is working. Okay? So, but then what we have is VDS and IDS, but this depends on VGS also. So just like for the BJT, whose characteristics, VI characteristics dependent on IB, base current, and we had multiple lines parallel, here also we have a similar situation where we have different lines. So if you have VGS equals to VT, you have that, right? So if you increase it further, there will be one value, another value. Likewise, you will have different lines. Remember, please note that I have not kept these distances equal. They are actually increasing. That's because it's a quadratic relationship. So if this is VGS1, let's say 1 unit above the VT, 2 units above the VT, and likewise, okay? VGS2, VGS3, VGS4, VGS5. So these parallel lines, blue lines, they represent the characteristic. It's not just one. Earlier you had something like this, but now they are completely different. They have straight lines which are parallel, and that depends on VGS as well. And this value parallel, meaning that on this IDS value is proportional to VGS square, actually. So something related to square. That is why the distance between these lines are bigger and bigger as you go up. Okay? So that's basically what you have there. And for this region, VDS is greater than or equal to VGS minus VT. The overdrive voltage. So this region here is cutoff region that we have been knowing, right? Cutoff. This is the cutoff region where VGS less than VT. That's been consistently like that, has not changed. But now we have another region here which we call saturation region. We haven't touched upon that so far. This is called the saturation region. Why is it called saturation? No matter how much you increase VGS, the ID doesn't change. ID is fixed, right? I increase the input voltage VGS, but current does not change. Current is constant. So that's the constant, the controlled current source. VGS is not changed. If you keep the VGS constant, the current is constant. So ID is constant. Sorry, what I said earlier was not correct. You change it's no matter what so voltage across it will change according to that, right? So VDS changes, but the current does not. So for a resistor, it doesn't happen like that. So that is why it is called saturation. So this is constant even when you change the voltage across the transistor output, right? So this is the saturation region. This is the area when you have this relationship between current and the input, the output current and the input voltage. So this is like you can control ID by using VGS. VGS is the input, ID is the output. So you can control a larger current using a small voltage, VGS. So therefore, this can be used to design amplifiers. So therefore, this region, the saturation, is very important in designing amplifiers. Obviously, it is not linear amplifier because the relationship is not linear, nonlinear. It's a quadratic equation, but nevertheless, you can use this, right? So this, if you take this value VT, if I draw a value like, if you draw a line like that, and if you assume this also represents VGS, this voltage here, not in VD direction, right? VGS. If you draw VGS and VDS in the same graph, then this is basically VGS minus VT. We call this V overdrive. And what you have here is square of that, 0 and square of that likewise. Okay, this curve represents the square of V overdrive. Okay, so and proportional to, right? So that is basically what you have. We call this region that is below this the triode mode. This is the triode mode. This is what we represented like a resistor in the previous section. Obviously, it is a little bit more complicated than a resistor, but we will see later. Okay. In the saturation region, both these conditions have to satisfy. That is, VGS has to be greater than VT, and VDS has to be greater than or equal to VGS minus VT. That is the overdrive. Drain to source voltage has to be more than the overdrive voltage. Then only it will operate in saturation region. Whereas in the triode region, in this region, triode region, what you will have is VGS is greater than VT, and VDS is less than VGS minus Vt, that is the overdrive voltage. Okay. So, VGS has to be greater than Vt, but VDS is small. Output voltage is in between 0 and overdrive voltage. Overdrive voltage is the one that designs it. Okay. Right, hopefully that is clear. Any questions? Clear? All right, let's move on. So, we looked at the input output characteristics. The next thing that we are interested about is the transfer characteristics. We looked at the VI characteristics. The next one is the input output characteristics, the transfer characteristics. So, in transfer characteristics, what you have is VGS, the input, V output, VDS, V out, right. So, that is my input output characteristics. We know up to Vt, up to threshold voltage, this is cut off, nothing has changed. So, therefore, output is VDD, that has not changed, right. That has to be like that. And what happens after that is what we are interested about. So, to obtain that, so we have the transistor like this. V out, V in. So, that what we are interested about this is IDS, this is VDS, this is VGS, like that. We know that V out, VDS is equal to VDD minus IDRD. But ID in this saturation region, IDS, VDS is equal to K over 2 VGS minus VT squared. So, I can replace it there, VDS is equal to VDD minus K divided by 2 VGS minus VT square RD, right. That is your relationship between VDS and VGS, input output relationship. So, what is this? This alone is a quadratic function, VDD minus quadratic function. So, 1 minus, right. So, it is a negative going quadratic function. So, this should look like, and when VGS is equal to VT, this value is equal to 0. So, therefore, that starts here, it starts here and it should go like this, right, quadratic equation going down, right, 1 VDD minus a quadratic equation, it goes like that. Does it go like that forever? It does not. At some point it has to change, right. We have to figure out where it changes. Actually, what happens is, after a while this gets into what is called the triode region. This region, we have not drawn the curves here, but if you can remember the transistor characteristics for the MOSFET, it was something like this, no? So, ID is less than that value, ID value is less than that. So, this what happens is this gets, as VGS increases, current goes to a certain value, and at some point it will be almost no voltage, right. So, therefore, this value gets saturated somewhere here. So, there may be some voltage here, but for the time being let us say something like that. So, up to what point does it behave then like this? We need to figure that out, but we know it starts from here. A is good, right. This point we know it exactly at VGS is equal to VT, this starts this behavior, quadratic equation. But when will it stop? But here it starts to kind of act funny. When is it happening? Now, to do that, in order to find that point, what we can do is, we know when that happens, VDS has to be equal to VGS minus VT. So, if you know this is VGS and this is VGS minus VT. So, whatever is here is V overdrive. Anything from here on is V overdrive. Square of that is what that determines this thing. So, if I draw a line 45 degrees like that, assuming these are in the same scale, right. So, this one is VDS is equal to VGS minus VT, because VT is minus. So, this is equal to that, okay. That is 45 degrees angle, this equation. So, this is basically overdrive, V overdrive voltage. At that point, beyond that point, so above this line, VDS is greater than that. This is VDS greater than V overdrive, correct. This is VDS less than V overdrive, correct. So, this is the VDS is equal to V overdrive. Above this VDS is greater, below this so below this it will not behave in the saturation region. So, this will only go up to this level, beyond that it will not. So, therefore, I can mark this point as my limit. So, the saturation will occur only during from here to here. So, this is the saturation. This is cutoff, and this one is triode region. That is a triode region. Okay. This is VGS less than VT. So, that definitely is, this part is cutoff, this part is saturation, this part is triode. This curve that you have here is basically that. That is the equation of this curve, right. So, this is the equation, that equation is equal to that. Questions? Thing to remember, or the more important thing is that this point occurs when VDS is equal to V overdrive, okay. So, that point beyond which it will not behave in saturation regimen. in saturation mode, IDS is a function of input voltage V in, and this is a voltage controlled current source. Voltage controlled current source. This is the control voltage. This is the current. So this is a voltage controlled current source. This can be used to design amplifiers. This can be used to design amplifiers. By changing VGS, I am changing a larger current I. Okay. This voltage, by sending this current through a resistor, you can convert that into a voltage. But in order for this to be used in this form, I can only, that equation is valid only this region, right? Only from here to there. If I am going to design an amplifier, if it goes outside this region, then it will not behave like an amplifier. So if I want it to be an amplifier, I need to ensure that it won't go outside this region, right? We call this a saturation discipline. We need to discipline ourselves to keep it within the saturation. Okay. So, but we need to ensure the MOSFET operates only in saturation region for that. In other words, ensure it is not cut off, VGS is greater than VT, greater than or equal to VT, and that it does not go into triode. These two conditions need to be satisfied, and we can do that. If we can do that, we call this saturation discipline. This is called the saturation discipline. We discipline ourselves to operate in the saturation region. Not just for a part of it, but all the time, throughout the whole operation, all the time, not just part of the waveform, throughout the time, throughout the voltages needs to be adhered to. Okay. So, in order to ensure this, what conditions should we ensure? Okay. So, let us look at that. What are the valid operating ranges? To ensure saturation. We know V in has to be equal to VGS, V in is the VGS, and that has to be greater than or equal to VT. That is one condition. Okay. As soon as we decide that, if you know the threshold voltage of this particular transistor, which we can get from the data sheet, okay, I need to ensure that the input voltage never goes below threshold voltage. Number one. How to do it, we will look at next, right. Also, V out needs to be And what is V out? It is the VDS. That needs to be greater than the overdrive voltage, that is VGS minus VT. In other words, this is the same as input voltage minus threshold voltage. This is one also known. So, we need to ensure that output never, output is always greater than this overdrive voltage. If the output goes below this, then during that time the circuit will not behave like a transistor, sorry, will not behave like an amplifier. Okay. So, we need to ensure that also. So, if you draw the circuit, what we have is a, in the saturation regiment, okay. In saturation region, what you have is, this is RD, this one is the IDS, which is equal to K divided by 2 VGS minus VT squared. And this is the input voltage. So, you have VGS, VDS output voltage, this is V in, V in is that, which is equal to VGS, output is like that, right. So, what is V out? We have already written this down. V out is equal to VDD minus IDS RD or RL, if you call this. I mean, I think in my note I have this RL, so let me make this RL. That's the load. That's the load, because I want the voltage through this, right, load voltage across that. So, IDS during this saturation regiment is K divided by 2 VGS minus VT squared. So, IDS from here, from this one, IDS can be written as, so let me, from this, right, from this equation, I can write IDS as equal to VDD divided by RL minus VDS, this is the output voltage, divided by RL. So, V out is equal to VDS. Using this, I am dividing everything by RL and taking ID this side and V, right. If I write it like that, so VI characteristics, right, we had earlier something like that, right. This is basically the IDS is equal to K divided by 2 V. Hold on. VDS squared, right. So, this is basically, this is a line. Why VDS? We know if VDS is greater than the overdrive voltage, it will operate in saturation region. This is this is basically a quadratic equation in this, and so we had these lines like that. VGS is equal VGS1, VGS2, VGS3, VGS4 like things, and we know this is the saturation region. That's a saturation region. Why this is like that? This line is ID is equal to K divided by 2 V overdrive squared, right? What is V overdrive? That VDS has to be greater than or equal to this. So, this equal sign is this, okay. Hopefully, it is clear. Right? So, this becomes this equation, right, this equation sign. On this graph, what you have is K divided by 2 VDS squared. Is it clear? Because remember earlier what you have, VGS minus VT, nothing to do with VDS. This is VGS, not VGS, this is VDS. Earlier the equation was ds is equal to k divided by 2 VGS minus VT squared. Now here what we are representing is between this and that, right? Okay, hopefully that is clear. So that's why we have, so this is on this curve, it starts to saturate. There is no VT on this line, okay, unlike in the previous case, right? So we know this is your cutoff. This is your cutoff. What is this? This is also another relationship between IDS and VD. When VDS is equal to 0, IDS is equal to VDD divided by RL. Okay, that point VDD divided by RS, maybe somewhere here, VDD divided by RL. When ID is 0, when this is 0, VDD is equal to VDS. In other words, VDS is equal to VDD, correct? And that's a straight line, so I can draw this straight line like that, okay? That's a representation of that. And this has nothing to do with your transistor. This comes directly from this application of Kirchhoff's voltage law into my circuit. It depends on the supply voltage VDD. It depends on the external resistor that I have connected here, RL, and the currents flowing in this thing. It doesn't give you anything about the transistor, right? Whether your transistor has, you know, some K value or not, it doesn't matter. This equation is valid no matter what, because this resistor and the power supply VDD is connected to the circuit. So it characterizes the external circuit or the load. So therefore we call this the load line. the load line of the system, the circuit, right? It depends on, it's nothing to do with the transistor, it's everything to do with the external circuit. External circuit defines this line, but this transistor is part of this circuit. So therefore, it has to obey not just the load line circuit, but also the transistor characteristics, right? So this transistor operates on this as well as that. It operates on that because it has to be part of that external circuit. It has to obey this characteristic because that's how it is designed. That's coming from its own parameters. So therefore, this has to be there. So though we have all this region to operate, it actually operates when you connect it in that circuit only in this small region, right? It has to be in saturation. So therefore, it has to stop here. So it starts with cutoff, that point is A. It has to stop, it should not go into the triode region. This side is triode, so therefore it has to stop here. Anything going above that, meaning that it will be going into the triode region, so should not. Okay, so it should be there. So this is my saturation region, this is your cutoff region, and this is my triode region. It should not go into that. So therefore, I have to stop here. I have to operate this within this region. Anywhere here is valid. It should not go into this. The saturation discipline, meaning you have to work from here to here, not anywhere else, right? So that's what it says. So in saturation region, IDS is below this curve. It's less than this K divided by 2 VD squared. Okay, so that has to be there. Because this is the input voltage, whatever it is. Let's say this is my input voltage V in. If I input this particular value of V in other words, VGS is equal to that particular value, let's say 5 volts, whatever the value that you choose. In that case, transistor has to operate on this line, nowhere else, because VG is that defines its characteristics. So it has to operate on this as well as that. So where is it operating? As soon as I know the V in, then I can say, it has to operate here, no other place. Can it operate here? Can it operate here? You can't. It has to operate here. So therefore, this point is the operating point. This is the operating point. And what is the input? What is the current? This is the IDS. And this is the VDS. That's the operating point. At that particular, if this is the input, these are the values. So let me put it in green. VDS, IDS. This has to be like that. Okay. As soon as you know the input voltage, now you know the output voltage, and you don't even have to make any calculations. This is a graphical method. So this is the valid operation, valid. So this yellow color curve, valid operating region, saturation. Once you connect it in a circuit, this is, though this whole thing is saturation region, I can only operate from here to there. Okay. So I know at A, IDS is equal to 0, VDS is equal to VDD, that's this value, VDD, right? We know that. Good. But then I need to know B also, so that I can only operate within these two values. So, what is B? What is this value and what is this value? That is the question, right. So, at B, I know IDS will be equal to, not less than, not greater than, it is on this curve, on this white curve, which is this one. It is equal to K divided by 2 V ds, which is squared, which is equal to K divided by 2 V out squared, because V ds is equal to V out. Okay, so, this let me call this, I have, okay, this is number 2. It is okay, let us call this one. The numbers are different in my note and this, but it is okay. But because it is on this yellow curve, IDS is equal to VDD divided by RL minus VDS divided by RL, which is also equal to VDD by RL minus V out by RL. Let me call this number 2. 1 and 2, let us, to be consistent with the notes, this is number 2 and this is number 1. Okay. This is because it has to be on this curve, this is because this has to be on this yellow curve, right. But what is V in? V in is equal to VGS, and we know this should be greater than or equal to threshold voltage, otherwise this will not be in the on state, right. So, this is something there, and we have to know this is in the saturation region. So, therefore, V out, VDS is equal to V out has to be equal to VGS minus VT. Remember earlier we had greater than, now we have equal, right. So, therefore, V out is equal to VGS is equal to VT, this will be, this is V in, or this is V in, right. VGS is equal to V in. So, this should be V in minus VT, that let us call this 3. So, V out is VDS, which is equal to VGS minus VT on this line. Okay. From 1 and 2, I can write. So, combining this and that, in other words, I replace IDS with this, so that IDS is equal to, ID is equal to, this is equal to that. Okay. I am going to put this right here, so that I will have K divided by 2 V out squared is equal to VDD divided by RL minus V out divided by RL. So, what you have here is a quadratic equation where you have K divided by 2 V out squared plus V out over RL minus VDD over RL is equal to 0. Now, what we are trying to figure out is what are the outputs that are legal or valid. Okay. So, therefore, V out is equal to minus B, which is minus 1 over RL plus or minus square root B squared, that is 1 over RL squared, minus 4 times A C. C is negative V already, so this becomes that VDD over RL divided by 2A. Right? So, we know this part is negative because RL is always positive. So, therefore, this part is negative. If this part is also negative, V out becomes a negative voltage, which is impossible because we have to work in the positive region because I have input as a positive voltage. So, therefore, this negative sign will not give me a valid answer. So, the only valid answer in this question, in this equation is this positive sign. It has to be there. So, therefore, I can say since VDS is equal to V out, it has to be positive, has to be greater than 0. V out at V has to be RL, I can take out, right, minus 1 plus square root of 1 plus 2k RL VDD. I am just doing some simple simplifications here. Please, follow that. I guess it's not that hard. West side RL times K. Okay. So that should be the V out. This is the value of the output voltage. Okay. So, at that point, V in at B is equal to Vt plus whatever that value, Vt plus V out. Vgs is equal to, because Vgs minus Vt is equal to V out or Vds. So, therefore, I have to add this to Vt to get Vgs. Right. So, you have this equation and you know both these terms. You can find this is equal to Vt plus minus 1 plus square root whatever that thing divided by RL K. Okay. So, that is that same expression, and IDS is equal to VDD over RL minus V out, which is that same thing, over RL. So, I can find that value also. So, in order to, so the valid input range, so therefore, the valid input range, I know already that V input or VGS has to be greater than V threshold, and this will give me a value the maximum value for VGS. So, this is the maximum input voltage that we can apply. So, this should be, that will give me V in should be greater than Vt, less than Vt plus minus 1 plus square root 1 plus 2k RL VDD divided by RL times K. So that will give me the range of values for this, and output voltage V out obviously greater than equal to 0, sorry, greater than equal to 0 and less than or equal to, from that you can get VDD has to be greater than, so VDS is equal to V out has to be less than or equal to VDD. It cannot be more than that. It can't go above the supply voltage. No? It has to be less than that, but it has to be greater than V out has to be at this point. This is that, so up to that value. So minus 1 plus square root of 1 plus 2k RL VDD divided by RL K. So that's your input and output limits. So that will give me the points on the transfer characteristics, because what you have is a transfer characteristic basically is a relationship between V in and V out. I know the value of V in and V out at both these A and B. So this is A, at A like that, at B like that. So I can define it easily. So let me leave it there and draw the transfer characteristics here. V out, V in, V out and V in. So I have Vt here, VDD, this is A, and it goes like that, and this is the 45-degree angle. This point is B, and from here on you will get something like that, right? And now we know the values of these two values we know. Those are the values here. These two are the values that should go in here, right? So V out, we have minus 1 plus square root that thing divided by K RL, and here this one is Vt plus minus 1 plus. That's that. Yeah, right. So those are the values. So we know the operating points. In order for this to operate in the saturation region, that's the saturation region. So we need to operate there. Since we only have one more page, I am going to cover this, otherwise we will have to take this to the next class. Just 5 more minutes or so. This is basically the switch unified mode, which is basically the main thing that we started with, the one that you have been doing, right? The nonlinear one. So let's quickly go through it and draw the VIN transfer characteristics and stop. Okay. This is the next model, switch unified. SU model. Now, in this group, this figure, if you look at this, it has some parts missing. In triode region, you don't have any curves. Now, earlier you had a triode like a straight line, resistor kind of thing. But even that is not here, no? We haven't drawn that here. So, in this model, we are kind of ignoring this. We are avoiding that from going into that region. But what if it goes? Then we need to know how it behaves in that region as well. So, that basically gives the MOSFET characteristics. That you have obtained or seen earlier. So, now we already have this curve. This is what you have seen. You have already seen this is the cutoff region, and these lines represent the saturation region. That's saturation region, and the triode region basically looks like this. That's your triode region. That's what was missing in the previous models. This is where you have a lot of nonlinearity. See, this region has a lot of nonlinearity. This is the triode region. And similarly, if you look at this is the VI characteristics. The transfer characteristics. V in versus V out. We know up to Vt it behaves similarly, and this behaves like a, up to this is the quadratic relationship, and then from there onwards it basically becomes like that. Okay. So, this is cutoff, saturation, is basically that, and this is triode. Okay. So, if I write a unified equation for IDS, now this becomes, for the triode region, I'm just going to give the equation, but I'm not going to derive it or anything. It will be this nonlinear region, this one. So, this area, okay, ID versus VGS, K VGS minus Vt, that is overdrive voltage, times VDS minus VDS divided by 2, squared divided by 2. This is for VGS greater than Vt, greater than or equal to Vt, that is in order to ensure that it is not in cutoff, and also VDS not in saturation means not greater than, is now less than VGS minus Vt, overdrive voltage. So, this is VDS is less than overdrive voltage. So, that is 1, this is 1, equation number 1. The second one, for this region we already know the equation, K divided by 2 VGS minus Vt squared, that is number 2. this is for VGS greater than VT, greater than or equal to VT, and VDS greater than or equal to VGS minus VT, overdrive voltage. Okay. So, both these things together here, yeah, and for the cutoff it will be 0. That is your full model, right. Full model is like that, and you can always find out the if you know the IDS, we can find out the V out easily, because it is equal to VDD minus ID R. Right. So, therefore, you can find both the output current as well as output voltage. Right. Okay. This concludes the section on any questions? Any questions up to this? Any part that you felt like, you know, I rushed through or made mistakes or anything like that? Please raise your hand and ask, and you will get points for that also. Okay. Right. So, with this we are going to move on to the next section. We said that in order to make this work, you have to ensure certain things, like for example, this has to be always working, input has to be more than VT, right. So, this is where we are going to go when we meet on Monday, which is called biasing. This section that we are going to start next week is called biasing. We are going to start there. I have already uploaded some recorded videos as well as lecture notes online. Please go through them if you have time, so that you can ask questions when you come. All right. So, if you don't have any questions, we can conclude our lecture here. Thank you.